Hi, I'm Sophia DAntoine, and today I'm going to show how you can use a new tool called Binary Ninja to do some more high-level program analysis and therefore better audit code. So what this talk is not about. I'm not talking about an amazing new analysis platform that's just going to print out bugs for you, but I'm not going to show how this tool is much better than others, but I am going to show how this tool makes a lot of things for code auditing and code review much simpler and allows you to use more research level program analysis methods to maybe audit everyday code or look for vulnerabilities. So what I'm talking about specifically is specifically for the current state of the art, you have a problem, and that problem may be you want to review your code for vulnerabilities, you want to review someone else's code, but you have a piece of binary that you want to look at. And this problem can only be solved with some tools depending on what you have. So either you have source code or you have the binary. And really depending on which of these two things you have, it opens up different levels of tools for you. So most of the time with source code, people end up reading the code, compiling the code with things like AFL and other fuzzers, using LLVM to compile it to LLVM bytecode, and applying some more advanced program analysis techniques on that. But that requires the source code. Now, if you only have the binary, so let's say you're reviewing a third party's program for vulnerabilities, the options are very limited. So right now, there are some different instrumentation tools out there like PIN and Anchor, as well as some static analysis platforms. But at the end of the day, we know that you're going to go straight to IDA. Why is this? It's because IDA allows you to first analyze the binary in a way that's interactive and tweakable, as well as customizable. So this means that you can open up the program and basically just read the assembly as you would source code. However, this is not perfect, and IDA isn't perfect. And the reason for that is that IDA can only show you what the computer executes. So it's showing you the compiled binary. And that may have a loss of information. Additionally, you can't use the output that IDA shows you to do more advanced research level program analysis techniques on it. So maybe you want to identify all the dynamically bounded mem copies, for instance. IDA does have a Python API, but how hard could it be? And the answer to that is very hard. IDA does not allow you to automatically analyze a binary or use different symbolic or program analysis techniques on it. So going back to our problem, we have a program that we want to analyze for vulnerabilities. What's the state for source code? So obviously, we're going to continue reading the code. This is useful. But a really strong player in the tool department for source code review is LLVM. And if, for those of you who haven't heard of that, LLVM stands for low-level, I believe, virtual machine or something like that. And it allows you to compile the source code into basically an intermediate language, which you can then automatically reason about. This allows you to apply a lot of different techniques onto the source code and do some pretty awesome things, like look for use after free vulnerabilities, which you can find on my GitHub, for instance. And I'm not going to talk too much about LLVM today, but for source code auditing and tool development, LLVM and reading source code just statically end up being the two most go-to solutions for people who want to analyze programs. However, in the binary department, like I said, what we're really left with is IDA. And we can't really reason about binaries the same way we can when we have source code using LLVM. So the majority of program analysis tools that are out there for binaries are extremely hard to use. They lack usable frameworks for interaction with your own analysis. So basically, it's very hard to write your own search queries, for instance, or your own your own analysis scripts on top of these binary platforms. So the tool I really want to talk to you about today is a tool called Binary Ninja. And yes, I did not make that name up. It's the real name. But Binary Ninja solves a lot of these problems in the binary world. So the main features of Binary Ninja are the Binary Ninja IL. And you'll see me use IL in the rest of my slides, and that stands for Intermediate Language. And that's basically when Binary Ninja can take the assembly that it produces from the binary and convert it into an intermediate language which you can reason about semantically. So kind of like sentences for a program. All right, so the basic structure of Binary Ninja, or shortened to Binja. It's based on a similar structure that IDA is actually. It uses recursive descent trees to recover the different, to recover the CFG of the program. And it displays it for you in the same way that IDA does. So from a static sense or point of view, Binary Ninja and IDA are pretty similar. And Binary Ninja organizes everything into expressions. So it takes the assembly and condenses what it can into something called low-level IL, or intermediate language instructions. And these things are basically like expressions in a program, which do one or more things. And these are side effect free, meaning when you reason about an intermediate language instruction or expression, you can know that everything you do based off of that instruction is basically everything that's going on at that point in the program. These intermediate language instructions are infinite length tree-based instructions, which means that they can be extremely large. So you have to take that into account when you're analyzing things with Binary Ninja. And it uses infix notation, and that's just more of a technicality. But it makes it so the destination operand is the left-hand side. And these are some more facts about Binary Ninja. Using their own intermediate language, they determine function ends using their own analysis as well. So it's basically like the tool already has its own program analysis passes written into the decompiler. And it does a little bit of symbolic analysis already to find the bounds of a jump table, which is pretty neat. So instead of having to write that yourself, it kind of provides that for you once it loads the binary into the program. All right, I'm going to skip this one because the picture got messed up. All right, so I want to show you how you could actually use the intermediate language API that Binary Ninja provides to make something pretty simple, a memcopy analyzer. So this would be useful if you're trying to find simple memory corruption vulnerabilities like buffer overflows. And I'm going to apply my little script on bin bash, just as an example. All right. So the cool thing about Binary Ninja is it allows you to reason about a program using their API, reasoning over all of the intermediate language phrases in this program. It allows you to do that completely from the command line. So unlike IDA, you don't actually have to load the program into the GUI interface. I have a lot of printouts there, but right now what it's doing, the reason it's taking so long, is it's loading the bin bash binary into Binary Ninja's backend, looking for all of the stack-based, or not stack-based, mem copies that I'm looking for, and printing out some information about those mem copies that I've requested. So I'm saying, I don't want to have to open this up in IDA to look for all the possible scenarios which could give me a memory corruption bug, but I want to be able to do this automatically through the command line without ever needing to open up the program at all, which is pretty awesome. So I don't actually have to know what this program does or know what it looks like in IDA or in Binary Ninja's CFG to know that there's these mem copies at these addresses. So the picture I have here is just showing in binary Ninja how bin bash would look. And I'm showing that I'm looking for all of these places where memcopy is called. So it's a pretty simplistic plugin that I'm running, but it's unique in the way that I'm going about doing it. All right, so one other cool thing about binary Ninja is it automatically tries to determine register states at the end of basic blocks in the program. And I think I will show this later on in a different demo, but I don't want to have to change my PowerPoint slide. All right, so here I'm walking through what my Python script looks like, just to show you how simple it is to use this API to find potential memory corruption vulnerabilities. So I'm loading a mock-O file here, and then this is me telling the binary Ninja API what type of program I'm looking at, how it should load it. And here I'm just saying it's from the command line. I'll open that file. And then I'm waiting for it to basically load into binary Ninja on the back end. And so the unique thing here is it's a headless API, which is really handy. All right, so here I'm looking for memcopies, and I'm just looking for this function called by its symbol name. You can also look for function calls by addresses and by different metrics that you want to use. Perhaps if you're looking at malware, you can also have binary Ninja tell you whenever something in a different segment is called or executed, or when a register is called, as if it were a function. So maybe if you're looking at obfuscated or packed code, you could use that. Right here, I'm just telling binary Ninja to, for every memcopy it finds, give me the function it's in, the address. So this is actually a unique thing about binary Ninja. Binary Ninja handles misaligned code, unlike IDA, which doesn't. So for every instruction, you not only have a function that it belongs to, like an LLVM, but you also have an address, unlike LLVM. And that basically allows you to have multiple instructions in the same function at maybe a different offset or something like that. So again, that's useful for misaligned code. All right, and then here at the bottom, I'm just printing out the destination of my memcopy, the source address, as well as the length n. And this is useful for just getting the simple parameters that are passed to the function. And this maybe allows me to see, for every case where memcopy copies something to the stack. And this could be useful for a simple program where potentially the mem copies to the stack, but where the length is larger than it should be. And this allows you to easily see all the possible cases where the length could be a problem. So I'll just show that. Destination stack. Oh no. And I was lucky enough that Bash actually has a mem copy to the stack to show this example. Oh, that actually won't work because I'm missing a colon. So you can imagine how this could save a lot of time for code auditing or vulnerability research, when you can simply look for all of your points of interest using a script like mine. So looking for points where a certain function is called with a specific argument, perhaps, or where a specific register is set to a specific value, or all these other metrics that you potentially look for when you do code audits, and then doing a simple grep for specific cases or addresses, or even values. And you can see here that there's 2 cases where bash actually copies stuff to the stack, and they're at these addresses, and this is the same one. It just printed twice. And then you can go take a closer look at that in Binary Ninja or even IDA. All right, so I showed you a little bit about Binary Ninja's API, but it's very robust. And that's because the developers of Binary Ninja actually went ahead developing a decompilation and disassembler based around the fact that they wanted an intermediate language API. So everything they built into this tool is meant so it's easy for the user to reason about the semantics of the code that you're decompiling or disassembling. And IDA was not developed this way. If anyone knows a lot about IDA or any other binary tools, they know that they were built around the idea of displaying the call graph of the assembly or something like that. And basically, it's not as easy to reason about. So Binary Ninja has Python, C, and C++ APIs. They are still in development with a lot of features. So if you talk to some of the guys there, they're more than willing to add a few functions to an API or add some other paths. But they're missing right now a way to traverse the call graphs of the function or of the program in a path, in a depth-first search manner. So basically, if you want to analyze a program where you go down every path sequentially, so every possible path sequentially, you have to do that yourself. But I wrote a simple template for that on my GitHub that you can use for that. Some other things that they're still working on, following branches is quite convoluted because not only do you have to iterate over the next basic blocks from the ending basic block, you have to know the function you're in, which can get tricky if you're working on misaligned code or other types of things. So Binary Ninja does have register state recovery to some extent, like I mentioned, which is quite useful because it might be able to tell you through some analysis that at the start of a function, EAX equals 0 or something like that. However, one thing that I'm currently working on is to basically recover ranges for variables at the end and beginning of basic blocks. And they also have quite an easy search engine to search the API, which I can show right here. So it's pretty easy. Let's see. There. And that just allows you to look at the API they have for it and the type of objects that you can use. All right, so I talked to you a lot about Binary Ninja and the API that it offers, as well as the fact that you can use that API to look for different patterns or different specific points of interest in a code. However, there's something cooler that we can use this API for, and that's symbolic execution as well as program analysis, which is more of a research topic, but you can use these things to very powerfully make tools that can then work agnostically over all the binaries that you may want to analyze. So symbolic execution, which was talked about earlier today, can be very accurate. However, it does take a lot of time and memory, so it's often not feasible to do. But we can reason only about what we care about. And using this API, we can make it so Binary Ninja loads the binary, and then we may only want to analyze function 1 or basic block 2. And we can do that with the API. So there's a lot of cool things that we can do with symbolic execution as well as program analysis, and I'm going to talk about that now. So program analysis. One element of program analysis is abstract interpretation. And this is a very research-oriented graph, so it's a little confusing. But what happens here is we take the points, all the variables perhaps in the program, or all of the different objects. And we can map all of these things, which can be very verbose and very complicated, to a simpler, smaller abstract domain. So we can say, well, all of these variables are of type int. And so we put those all in the same int bucket. And all of these are doubles, and so they all go in the double bucket, and so on. So we can reduce the states of our program to be something simpler. And that's our abstract domain. And in the research world, this is called the Galois connection, when you can map things from the concrete or more complicated program to an abstract, simpler domain. So what we actually want to do with this is make reviewing code easier. So this is a little diagram of how when Binary Ninja or IDA loads a program, and you're looking at the program, you're 10 functions deep, what starts to happening is you start to lose details or information about specific variables. So here, as we're walking through the program, we may know all of these things at the beginning about variable x and variable y. But by the time we get down here, we know nothing about a except that it's a variable. So obviously we're very sad. So using abstract interpretation, we can reason about the program, so make a script to reason about it, and symbolically execute different parts of it, mapping our variables into our abstract domain. So let's say we're looking for the types. We want to recover type information. And so we can actually recover the fact that a might be an integer, which is extremely useful when reviewing code. And if we want to know more and use a bit more symbolic execution, we can actually recover things like signs. So maybe we can determine that x and a are both positive at certain points in the call graph. And this is useful because there may be branches which only happen if z is negative. However, if we know that z is always positive, we know that that branch is never taken, and we can ignore looking at that half of the call graph, saving us a lot of time. And this goes for many different scenarios where this information would be useful. All right, and this is just a simple example of a small program that doesn't really do anything. However, when we're analyzing it, looking for potential vulnerabilities or bugs, we really can't determine much here, especially using program analysis. So one thing we can do to solve this problem, because x is imprecise, is determine a small range for x. So let's say we know x is an integer. We know that if it's an 8-bit integer, it can only be from 0 to 255. And if it's signed or unsigned, that gives us more information about the potential bounds of that variable. So for this example, I was giving it a small range. So let's say x can only be between 0 and 9. Even then, when we're symbolically executing the code with these bounds, we can see that 2 times x could potentially be greater than 10. And therefore, this move of 3 into that memory address could actually be invalid. And so compilers do a simple level of this as well. And it's very imprecise, but it does find a lot of things. So maybe when you're compiling your code with GCC or Clang, you might get some errors like this, like out of bounds exceptions or unchecked bounds. And this does require some control flow analysis, but that inherently is given to us when we walk through a program symbolically. All right, so a more complicated example of how we can use abstract domains is this program here. So here we know the concrete values of A and B. And if we know that if there's some input, C is either A plus B Or if there's no input, C is A minus B. So if we symbolically execute this, we have to go down both paths because we don't know what that input could be. So in our abstract domain, I create 5 different values. And this is just standard for sign analysis. Sign analysis passes. You have 0 for if you know something is 0 or not. Negative, positive, obviously, because it's signed. Question mark, because you don't know. There's potential cases where you just can't recover a possible sign for that variable. And this symbol down here, which I do not know how to pronounce, but that would be something where that might be a pointer or not an integer or something like that. And so what we can do here is actually recover that in 2 different cases that we have, input or no input, C is either positive or negative. So using this abstract domain for sign that we have and binary ninja, we can actually have it printed out maybe in comments or something when you're viewing it in the GUI that C is positive here and negative here. And that can be useful when reviewing code or looking at a larger call graph where you may not be able to symbolically execute everything in your brain. All right, so what I wanted to do with binary ninja after I wrote the memcopy example that I showed you was do something with this sign analysis. So what I wanted to do was be able to right-click on a function and be able to recover all of the signs that I could from the function for all the variables, if they could be recovered at all. So what I did for my pass, which I'll show you in a second, is under approximation, and that just means that if I don't really know something, I don't guess. So I don't want information that's a false positive. It's path sensitive, which goes back to my example of this code snippet here, where in certain cases, C may be positive or negative down different paths. And this means that if it wasn't path sensitive, C would be positive and then unknown for the second one, and I'll show that in a second. And one abstract state per CFG node, and that just basically means that for every variable that I'm looking at, I want to be able to map it into one value into my domain. And then I avoid loss of precision in fractions. And this just means that I introduce a positive 0 and negative 0, so it's not that important. All right, so I'm going to show my demo, and what I'm going to show it on is PHP, actually. This is a CVE from this year. And using my tool, you can actually see the case where the register values being passed around are actually incorrect. And there's a type confusion bug that you can discover using simple sign analysis. All right, so this is, well, I'll show this one first. So I'm going to run my sign analysis script on this program. It's very simple. This program is actually the same one that I used to show the example with C being positive or negative. So if you make a plugin for Binary Ninja's GUI, you can actually just right-click, do sign analysis here, and get these awesome comments. So right here we see that we know that EAX is positive here. This add sets EAX to positive again because we're adding a positive net value. So we symbolically know that a positive plus a positive equals a positive. So variable C is positive. Now this is not path sensitive. This example isn't. And so that means that we execute down this path first. And by the time we get to this path, we have C being positive already in our storage of variables. And so we have a positive subtracted by a positive. So without actually executing that subtraction, we may have to say that C could be 0, depending on how large var 18 is. And so we just say that C is unknown. So this is the PHP function, and it's quite large. So clearly we don't want to have to go through the effort of looking at everything there. And it takes a bit of time to run on everything. Awesome. And so you can see that my plugin is recovering types when it can. And it's not completely done yet. I haven't implemented some registers. But we know that, for instance, R15 came from perhaps something being passed to the function. So we can't say anything about that variable, nor R13. But as you move down, I'm trying to find it. You can see that we're recovering some type information. And we can also look for different things. So for instance, in this case, there's also a call to memcopy. And we know that we know certain things about libc's memcopy. We know that it does a sign extension cast to the things that are passed to it. So we know that if something is signed being passed in, it becomes unsigned. And this is vulnerable to type confusion because the registers being passed to this function, we can recover that they are unsigned. And we can do that using additional type recovery information. And that's also in my tool. All right. Oh, one thing I also wanted to show was that. And this is just the lifted IL display. And that gives you basically what you're reasoning about, but it gives you a bit more information. All right. So all my scripts are available online, including my sign analysis one, as well as unsigned versus signed type recovery, and the memcopy script that I showed you, available on my GitHub, as well as the Trail of Bits GitHub. You can contact me an IRC, email, the Binary Ninja Slack. And in conclusion, I'd like to thank Vector35, who is the founder and creator of Binary Ninja, and for answering all my questions there. My company for letting me do a side project. These are different resources I used. I really recommend the last one. It's literally the best static analysis book that I've ever seen online, and it's just free. So if you are interested in the topic, definitely check that out.